Okay, good morning, students. Let us discuss about a root locus technique. Okay, root locus is nothing but it's a graphical method that is used in a control system in order to show how the closed loop goes or moves in the complex way. Such as in order to determine the system parameter, usually the gain, how the gain is varied. Generally, what's the purpose of root locus means? It determines your system stability and it also shows how the gain will be changing based on the pole location. And it also helps in designing the controller, and also it also helps to analyze how the performance of the system is. Okay. Then what is the advantage is that it is a simple graphical technique and it provides the information about stability and transient response. That is the main advantage of the root locus technique. Okay. Then we are going to study about the time and frequency domain consideration. What is meant by time domain analysis is nothing but it shows how the signal will be changing with respect to the time. It's a time domain analysis. Its main focus is that the signal amplitude versus that is if you plot a graph means that is the signal amplitude is in the y-axis versus the time in x-axis. That is the main difference. And the important parameters in the time domain analysis is that rise time. That is how the signal will be varied from 0 to infinity, like that. It's a rise time and a peak time, that is a PP, and settling time, TS, overshoot, MT, and it is used to determine the steady state error. Okay. Then these are the key features. What are the applications is that it is very useful for analyzing the transient events, and it is very useful in real time processing, and when the computational resources are limited. Then is frequency domain analysis. Frequency domain analysis is nothing but it studies the frequency components. How the frequency components is present in a signal is a frequency domain analysis. The main focus is that is a signal amplitude. That is, if you plot a graph means that is frequency on the x-axis and the signal amplitude on the y-axis. That is the main difference between time domain and frequency domain. Then we can calculate the performance of the system at a different frequency. Then the important parameters in frequency domain analysis is that gain margin, gain margin, bandwidth, gain margin. That is, gain margin is expressed in terms of dB, decibel, right? So phase margin is expressed in terms of degrees, and bandwidth. Bandwidth is the difference between upper cutoff frequency and lower cutoff frequency, resonant frequency. And important tools are used to determine the time domain and frequency domain analysis, that Bode plot, Nyquist short, etc. This is the main difference. And time domain analysis, that is transient event in time domain analysis. Time domain analysis is preferred when the signal changes rapidly or unpredictably with respect to the time. In this cases, we are going for a time domain analysis. For example, switching circuits. For the switching circuits, pulse signal, startup and shutdown behavior. Why the time domain analysis is used? Means it directly shows how the signal varies or how the signal changes over a time. It helps to measure the rise time, settling time, and overshoot time. I have already told that, right? So periodic signal. Next is periodic signal. Periodic signal is it comes under the frequency domain analysis. It is very more suitable for the signals that repeat periodically. For example, that is a sine wave, cosine wave, that is a audio signal, etc. Why the frequency domain analysis preferred means it reveals the dominant frequencies and harmonics, and it makes the periodic behavior easier to analyze. That is the main difference. And next is filtering and noise reduction. It also comes under the frequency domain analysis, and it is widely used to remove the unwanted. What is the main use of filter? It's used to remove the unwanted noises and extract the useful information, right? So that is the main concept here. So what are the example is that it's mainly used in, that is a frequency domain analysis is mainly used in communication system. and image processing, biosignal processing, etc. Why frequency domain? Why the filtering and noise reduction consider the frequency domain is that noise often exists at specific frequency. In order to remove those frequencies, we are using a filter. So next is system stability. System stability comes under a frequency domain analysis. It is widely used to determine how the control system stability is, and especially with the feedback. I have already told that there will be the two feedback. One is positive feedback and negative feedback. Positive feedback is that the output signal will be giving a feedback to the input with in phase with the input signal. That is a positive feedback. And negative feedback is that the output signal will be given feedback to the input signal with the out of phase. That is a negative feedback. Okay. Then why it is important is that it helps to predict whether the system remains stable or not. Then is computational efficiency. Computational efficiency is that in many situations, the frequency domain analysis can be more efficient than the time domain analysis. Why it is so? The complex signal can be broken into simple frequency component. That is, if one block is that means it will be breaking into the simple blocks. Like that, the complex signal can be broken into simple frequency components. That will be processed by the signal processor. That is such as filtering, like that. So the mathematical calculations are simplified, more often simplified in the frequency domain. That's why we are going for a frequency domain analysis. Then let us see the application. It's used in a digital signal processing, that is a DSP, audio processing, image processing, and communication system. This is an overview of time and frequency domain analysis. Then, time and frequency domain compensation, that is a compensation techniques or other methods used to reduce the distortion or errors or unwanted signals in the system. These techniques improve the signal fidelity, that is, it is used to improve the signal strength, stability, accuracy, and overall performance of the system. It is mainly used in a communication system, signal processing application. These are the advantages and disadvantages. And for the filtering, I have already told that filtering is used to remove the unwanted noises in order to get the useful information. That is the main use of filtering. FIR, IAR. You have already learned it about signals in system, right? So, in order to attenuate or amplify the frequency components, we are using these filters. There are different types of filters, that is a low pass, high pass, band stop. What is the use of low pass filter? It's used to allow the only low frequency signal. It blocks the high frequency signal. What are the applications of filter? It's used in audio processing, communication system, biomedical signal processing. Then equalization. Equalization is nothing but it adjusts the signal amplitude and phase to compensate for the distortion introduced by the signal system. That is the main use of signal equalization. What is the purpose is that it's used to restore the original signal shape, and it reduces the signal distortion and improves the data transmission quality, and it will minimizes the ISI. ISI is the intersymbol interference. Where it is used means it will be used in a wireless communications, optical communications, audio system, etc. Then frequency domain compensation. Frequency domain compensation is that I have already told you. It's a signal processing technique. It's used to improve the signal quality by modifying the signal frequency spectrum. Instead of working directly with the signal in the time domain, the signal is transformed into the frequency domain where the amplitude and phase characteristic can be adjusted with the function of frequency. This approach is widely used in communication system, audio processing, and DSP application. FFT is nothing but fast Fourier transform, and IFFT is the inverse fast Fourier transform. These are the advantages and disadvantages. And let us see about the power amplifier. Okay. Power amplifier. Power amplifier is nothing but it will convert a low power signal to the high power signal. There will be the two common examples of audio amplifier. Audio amplifier is nothing but it's used to drive the loudspeakers and headphones, and RF power amplifiers. It is used in the final state of a transmitter. That is, it is used in generally the power amplifier is used in a transmitter itself. That is, the signals will be processed and it converts a low power signal to the high power signal. That is the main concept here. Okay. It is mainly designed for amplifying the audio signal. Okay. Then there are the different types of power amplifier. Audio power amplifier are designed to amplify the audio frequency signal, especially typically that is 20 hertz to 20 kilohertz. That is a audible frequency, right? So it's used to amplify those signal. That is a audio power amplifier. Where it is used means it's used in a loudspeaker, headphone, public address system. Then RF power amplifier. RF power amplifiers are designed to amplify the radio frequency signal before the transmission. Okay. Applications of RF power amplifiers are radio transmitter, television broadcasting, satellite communication, wireless network. These are the two types of power amplifier. These are the two types of power amplifier. What are they? First one is audio power amplifier, radio power amplifier, RF power amplifier, DC power amplifier. DC power amplifier is nothing but used to amplify pulse with modulation signals. PWM is nothing but pulse with modulation signals in electronic control system for high power motors or actuators. Then let us discuss about Class A power amplifier. Power amplifier is also called a Class A amplifier. Okay. It is a type of power amplifier. Class A power amplifier is a type of power amplifier in which transistor conducts for the entire 360-degree for the input signal. If the transistor remains on throughout the input signal, the output signal is an accurate amplified version of the input signal. Okay, is it clear? Yes. Class A amplifiers are widely used in high signal fidelity and low distortions on rectifier. Let us see the overview. Power amplifier is otherwise called Class A amplifier. It is used if the transistor used in the circuit conducts for 360-degree. Okay. Q point is the operating point or present point. Is selected approximately at the center of active region of the transistor. Okay. Then here there will be ID equal to IDC plus IRF sine omega naught t. This is the equation for power amplifier. IDC is nothing but bias current and high RF is a signal current. Okay. And the sine omega t is, that is signal current is varies with respect to time. High RF is a signal current. It represents the amplitude of AC signal component of drain current. It varies according to the input signal and it produces an amplified output signal. IDC is a bias current and RF is the amplitude of signal component of the drain current. And that is transistor. Here, the transistor conducts for 360-degree of the input signal. That is excellent linearity. It will give excellent linearity and a very low distortion, high signal fidelity, and simple circuit design. That is, linearity is excellent, simple, the efficiency is very low. Simple circuit design. Why the efficiency is very low means due to the continuous current flow, so there is an efficiency is very low. Then applications is that high fidelity audio and low noise status. Here, the Class A amplifiers will be used. And Class B amplifier. Class B amplifier is a power amplifier. It's also a power amplifier in which transistor conducts for. Here the Class A amplifier will be conducts for 360 degree. Here the Class B amplifier conducts for 180 degree of the input signal. To amplify the complete waveform, the two transistors will be used in a push-pull configuration where one transistor amplifies the positive off cycle and other amplifier amplifies a negative off cycle. That will be the two transistors will be used. Okay, yeah. One for positive and other for amplifying the negative off cycle. So the conduction angle is 180 degree and the operation there will be two transistors will be used. The efficiency is here higher and linearity is a very good but less than class A and applications is a RF and radio but AB correction and class AB. Let us see the class AB. Class AB is nothing but it's also a power amplifier. It combines the advantages of both Class A and Class B amplifier. The transistors are biased slightly above the cutoff point. That is, it allows the transistor to conduct for more than 180 degree but less than 360 degree. That is the main difference here. So the operation, that is, the transistors are biased just above the cutoff to reduce the crossover distortion and efficiency is compromise between Class A and lower than Class B. And linearity is better than Class B. Okay. Applications is that that is Class AB amplifiers used in audio amplifiers, power amplifiers in radios. And Class C amplifier. Class C amplifier is a power amplifier in which transistor conducts for less than 180 degree. This is very important. We have to know the conduction angle for all the amplifiers for Class A, Class B, Class AB, and Class C. Okay. For the Class C amplifiers, the conduction angle is 180 degree and it operates only a short path. That is, the transistor conducts for less than 180 degree of the input signal. Okay. We have to remember this. And the transistor remains off for most of the cycle and conducts only for a short duration. The efficiency is very high, typically 80 to 90%. Linearity is very poor. In Class A amplifier, the linearity is very excellent, but in Class C amplifier, that is very poor. Applications is that it's used in RF transmitters, not in audio, it's used in RF transmitters. A main advantage is that very high, it gives a very high efficiency and low power dissipation. It is very suitable for high frequency operation. Next is Class D amplifier. Class D amplifier is the operation uses a pulse width modulation, PWM. And the transistor here, the transistor will be acting as a switch, that is on or off. Okay. That is unlike Class A, Class B, Class AB amplifiers. The transistor in Class D amplifier act as a electronic switch. Which amplifier will be acting as electronic switch? Class D amplifier. It operates in on or off state. So the main advantage is that it gives a very high efficiency and low power losses and the compact size and lightweight design. It gives a longer battery life with portable devices. Main applications is that it's used in audio power amplifier, portable speaker, battery powered system. And Class E amplifier. Class E amplifier, it uses as a switching transistor and resonance circuit. It's a highly efficient switching mode RF power amplifier. Okay, so Class E amplifier is a very highly efficient switching mode RF amplifier. It's very used in highly frequency application. Okay, efficiency is very high, typically greater than 90%. And the frequency range is suitable for high frequency, that is megahertz to gigahertz. And design is very carefully designed load network and zero voltage switching, that is ZVS. Applications where we are used is RF transmitters and wireless power. RFID system also we are using the Class C amplifier. Next one is Class F amplifier. Class F amplifier is a highly efficient RF power amplifier that uses harmonic tuning and resonant networks. Harmonic tuning and resonant networks. Why we are using harmonic tuning and resonant networks? In order to shape a voltage and current waveform. That's the main point here. Yeah. By controlling the harmonic frequency or switching losses are minimized, that results in a high efficiency. And applications is that it's used in very high frequency RF transmitters and satellite communication system, wireless communication system, etc. And this is the main difference between different types of power amplifier, that is class A, B, class A, B, class C, D, E, and F. Yeah, the radio frequency power amplifiers are widely used in are essential components in wireless communication system. This is it's nothing but high output power is necessary. That is important in order to achieve a long communication distance and reliable signal transmission. Non-linearity in RF power amplifier. That is, output of RF amplifier should be perfectly amplified version of input signal. Feedback linearization. Feedback linearization is that it's a technique in order to reduce the distortion in RF power amplifiers by applying a negative feedback. What is mean by negative feedback? That is a part of the output signal will be given back to the input in order to reduce the, part of the output signal will be given to input signal, that is out of phase with the input signal. That is a negative feedback. So feedback linearization is a technique in order to reduce the distortion in RF power amplifier by applying a negative feedback. Okay, that is the main concept here. And this helps to correct the amplifier non-linearity and improve the signal quality. Okay, two types of feedback here: the voltage feedback and current feedback. Voltage feedback is nothing but that is a portion of output voltage is fed back into the input. So current feedback is nothing but the portion of output current is fed back to the input. Okay. In voltage feedback, it's commonly used in amplifier circuits. Current feedback also it's used in high-speed amplifier design. The advantages is that it reduces the harmonic distortion and stabilizes the gain. Disadvantage is that limited bandwidth in RF frequencies due to delay and phase shift. Feed-forward linearization. Feed-forward linearization is a technique that is used in a RF power amplifier in order to reduce the same adeda. Forward, that is a feedback linearization is also same, and feed-forward is also similar concept. These also used in RF amplifier in order to reduce the distortion. Concept is that the distortion generated by the main amplifier is extracted and the phase inverted distortion signal is created. That signal will be amplified and subtracted from the output so that we can get the distortion components. So the main block is the main amplifier, error amplifier, delay lines. Main amplifier is that it amplifies the input RF signal and it produces both the desired signal and distortion signal itself. Error amplifier is nothing but it amplifies only from the name itself, we can say that it amplifies only the extracted distorted signal. It generates a correction signal. And delay lines is used to synchronize the main signal and error signal. It's used to ensure the proper phase alignment for distortion cancellation. That is the main concept. And where it is, these are the pros and cons of feed-forward linearization. These are mainly used in RF power amplifier, satellite communication, microwave communication. Next is pre-distortion, that is digital or analog. Main concept here is that is it's a technique is used to improve the linearity by applying a inverse distortion. Okay. When the pre-distorted signal passes through the non-linear amplifier, the amplifier, what is the use of amplifier? It will amplify the signal, right? So When the pre-distorted signal passes to the non-linear amplifier, the amplifier distortion cancels the applied inverse distortion. This results in a linear output. The that is a that is both the x-axis. If you plot a graph, means both x-axis and y-axis, it gives a linear output. So two types of pre-distortion, that is analog pre-distortion and digital pre-distortion. Analog pre-distortion, that is implemented using analog circuit, and for digital pre-distortions, the implemented using the digital signal processing, that is a DSP. And next is envelope elimination and restoration. Envelope elimination, that is, it's used to separate the envelope. It's a linearization technique. It's used in RF amplifiers in order to improve the efficiency. The input signal is separated into its envelope, that is amplitude and phase component. These components will be amplified separately, and lastly, it will be recombined in order to produce a final output signal. The bit will be separated into blocks, then at last it will be recombined in order to combine a final output. These are the pros and cons of envelope elimination restoration, that is EER. Where it is mainly used is, it's mainly used in communication system, that is wireless communication system. It produces a high efficiency, that's the main advantage. And next is linear amplification with non-linear components, that is LINC. LINC is linear amplification using non-linear components. It's a linearization technique that's used in RF power amplifier in order to achieve both efficiency and linearity to be very high. Here, the input signal is separated into two constant envelope signal, and it will be amplified independently. That is, it will be amplified independently. We are getting a two signal using a efficient non-linear amplifier, and then we have to combine to reconstruct the original signal. That is the concept here. Advantages is that it gives a high efficiency and linearity is very excellent. What are the disadvantages? That the combiner losses reduces overall efficiency. That is a main disadvantage. And Doherty amplifier. Here, the Doherty amplifier is a high efficiency RF power amplifier. It's widely used in modern wireless communication system. Generally, it employs two amplifiers, namely main amplifier and peaking amplifier. Main amplifier is a carrier amplifier and peaking amplifier. Why we are using two amplifier means in order to maintain a high efficiency and good linearity over a wide range of output power levels. The concept is that two amplifier. What are they? Main amplifier and peaking amplifier. The main amplifier will operate continuously at low and medium power levels. But in peaking amplifier, whenever it is turned on only when the higher output power is required. Applications that we are using in satellite communication system. This is a comparison table of different types of amplifiers and different types of linearization technique. That is a feedback linearization, feed-forward linearization technique, pre-distortion technique, EER, LINC, and Doherty. Kindly refer this. And ACPR. ACPR is nothing but adjacent channel power ratio. It's mainly used in RF and wireless communication system to measure the amount of signal power that leaks from transmission channel. That's the main concept. It is widely used to evaluate linearity and spectral performance of RF power amplifiers and transmitters. That is, ACPR is a adjacent channel power ratio. It's a ratio of power in the adjacent channel to the power in the main channel. That will be the two channel adjacent ratio of power in adjacent channel to the ratio of power in the main channel. That is a concept here. Applications is a satellite communication, radio broadcasting system, etc. The main purpose of ACPR is that it measures the spectral regrowth due to the non-linearities in RF components, and it will indicate the interference, that is a signal to noise ratio. What is meant by SNR? The ratio of signal power to the noise power. Then that's very important in the systems like LTE, 5G, Wi-Fi, etc., where the spectrum efficiency is very critical. Then lower ACPR. Lower ACPR, that is more negative dB, indicates better transmitter performance. It indicates a better transmitter. If it is negative, means it indicates better transmitter performance. Then applications is that power amplifier linearity testing, that is used to evaluate the linearity of RF power amplifiers, and compliance testing, that is used to verify the compliance with spectral emission standard. And next is digital pre-distortion, that is DPD. We have already learned about that. So last one is wireless communication system. These are the applications. Then typical setup. It generally uses a spectrum analyzer in order to measure the power. There will be the two channel. I have already told that adjacent channel and main channel. And ACLR. ACLR is the adjacent channel leakage ratio. And EVM is the error vector magnitude, and OBW, that is occupied bandwidth. Thank you.